Good evening, everyone. If you're in Saudi Arabia, and good afternoon if you're in College Station, Texas. And thank you all for attending today's seminar. Actually, today we have a very distinguished speaker with us. But before I start, let me first acknowledge um, the renewable energy and the hydrogen mobility concentrations of the chemical engineering department, as well as the AICHE student chapter and the Young Professional Committee of the Saudi Arabian section, AICHE, for co-organizing the seminar with us and helping us with all of that. As I said, today we have a very distinguished speaker. He is Professor Stratos Vistopoulos from Texas A&M. Professor Stratos is the director of Texas A&M Energy Initiative, and he is also the Dow Chemical Chair professor in the Chemical Engineering Department and Texas A&M. Before joining Texas A&M, he stayed for around 16 years as a professor in Imperial College, London, and before that he worked in Shell Chemicals. He was also the director of the Process Systems Engineering, PSE, in the UK, as well as currently the Texas A&M Principal Investigator of the Rapid Institute on Process Intensification. He holds a PhD degree from Carnegie Mellon University and published more than 500 research papers on modeling, control, and optimization of processes and energy systems. Among many prestigious awards, he recently received the Mac Robert Award from the Royal Academy of Engineering. He's also currently the editor-in-chief of Computers and Chemical Engineering, one of the top Q1 journals in the field. So without further ado, please join me in welcoming Professor Paulus, and thank you very much for joining us today, Professor.
Thank you very much for the very nice introduction, and I'm delighted to be able to give a seminar at the King Fahd University. I always wanted to visit, and I hope I will have Can you all hear me?
Yes, right now we can hear you, Professor.
Something went wrong, so I'll start all over again. I was just saying how thankful I am and delighted to be able to give the seminar at the King Fahd University and the department there. And as we highlighted earlier, this is the beginning of a new era of exploring collaborations in the future. So I will talk a little bit about multi-scale energy systems engineering and define what I would like to say. But before we do this, let's see if this moves. I just want to first provide a very short overview of the Energy Institute of Texas A&M that I'm the director of. A little bit, just at a glance, the activities, the research activities I'm involved with my research group, and then I will focus on aspects of multi-scale energy systems engineering. I will try to define why we need a systems approach, when we're dealing with the energy challenges of the future, and then I will demonstrate this with two big research topics and areas, one on process intensification and one talking about energy transition strategies. So a little bit about the Texas A&M Energy Institute. I just want you first, can you all hear me, by the way?
Yes.
All right, that's good. So we have approximately 270 faculty affiliates with the Energy Institute, for across the spectrum of energy research activities within Texas A&M system, not only the Texas A&M campus here, but also the various branch campuses and other member institutions. And the key philosophy of the Energy Institute that we take this systems-wide thinking and structure to be able to empower the energy solutions of the future and improve quality of the life. The way we are structured is that we take a panoramic view of the various components of the energy, if you wish, value chain.
Professor?
Yes?
Can you share your screen again?
All right. Let's see. Where is this? So you cannot see my slides?
Not now.
Uh-huh. How we do this? Why I don't get the... Just a moment. I apologize.
That's okay.
Why I don't get the Zoom? All right. There I am. You were only looking at me, right?
Yep.
All right. Okay. How about this?
It's shown now. Great. Thank you.
Now it's okay.
All right. I apologize.
It's okay.
Okay. Zoom, it's a great technology. It's becoming better and better, but obviously it's not perfect and nothing can substitute physical presence, in my opinion. Anyway, so I was talking about the Energy Institute, and it takes a panoramic view of the energy research issues across the board. So on technologies for energy, both fossil and non-fossil, including nuclear. Then we look at the materials, like agents, which enable or will play pivotal role in enabling future energy solutions for clean energy, like catalysis, clean catalysis, and so forth. The criteria that drive the energy revolution, like not only economics, but also law, international policy, national and international policy, societal impact, sustainability, climate change, the law. And then the glue, and that will be the topic of my presentation, the glue that connects the technologies, the materials, the agents, the various criteria, the societal impact, safety, environmental impact, and so forth, is what we call multi-scale energy systems engineering, and we'll clarify this along the seminar, and this will be my main thesis of the seminar. And this is pretty much the philosophy of the Energy Institute here. So we have a big program on the research front. We have a very novel master program and external relations. Just one slide on our Master of Science in Energy. This is a fast track, panoramic type of master program. So we don't go in depth in a particular, so it's, if you think about it, all the master programs are, let's say, domain driven, like chemical engineering, petroleum, or chemistry, so forth. We don't do this. We take a horizontal view of the energy aspects. So we try to train within a year or less than a year, in fact, our students on technologies for energy, on materials for energy, but also on the societal drivers for energy, business, finance, the policy, energy law, as well as the glue that I was talking about, this multi-scale energy systems engineering that we need to develop and understand quantitative analysis in order to be able to make this connectivity. And that's just for you to get a feeling of the various partnership-based initiatives that were involved. Just the two that I would like to mention, perhaps, is those two at the left-hand side corner. Those are Manufacturing USA big institutes, one on process intensification under the auspices of the American Institute of Chemical Engineering, and this on the digital twin, let's say on smart manufacturing kind of technologies, like digital technology empowering physical technologies. The SESMI Institute, which is under the auspices of University of California, Los Angeles. Both are DOE, Department of Energy, big initiatives. And the other perhaps, so we have a big program on, this is DOE for women leaders in energy, the Clean Energy Education and Environment Initiative. This is together with MIT and Stanford and various other activities that you can see here. So that's on the energy issue side. This is my personal research group, and just for you to get a feeling of the areas we are currently working here, you can see the various funding agencies that support our research. A lot on multi-scale energy systems engineering. I'll talk about mostly on the energy transitions, process intensification, smart manufacturing. I'll talk a little bit about process intensification as well. And then if you wish, one of my bread and butter fields of research is the whole area of multi-parametric optimization or control that we apply at different scales and different applications. So, and let me switch now on the energy systems engineering approach. So I don't think I will go fast through those slides. The key point here is that as the world economy grows, the world will demand more and more energy, and this is a staggering figure of projection. We're talking about 1,000 exajoules in 2100. All right, and I think this is, the scale of energy is something that energy demand is something we need to keep in mind. So the key question is, where do we get currently the energy from? And what are the future trends, kind of? So it's needless to say, we all know this, despite the rhetoric and the whatever, the data and numbers show that still, pretty much we're getting most of our energy from fossil fuel. This is a reality, all right? And this is just a plot, just to see, this is from the AI, where you can see, this is the sources and this is the sectors that consume this energy. So fossil fuels still help us power the world and provide, so not only the energy, monetary ways, but also form the basis of our chemical feedstocks, right? Okay. So yes, renewable energy is becoming efficient, more and more efficient and cheaper, and all, but still this is where we are, all right? But obviously, at the same time, while we accept that at the moment the energy mix is predominantly fossil fuel based, we need to think carefully for in the future and address issues related to the environment. Another staggering feature, if you wish, a number is, here, the amount of CO2 that we're emitting per annum is staggering, 30 billion tons of CO2. All right, and CO2, okay, it accounts for almost 75% of the greenhouse. It's not the only concern. Methane is another major concern, but clearly, we need to do something about the sustainability of the planet, if you wish, of our lives. And we need to change somewhat this picture and think about the transition as we go from 2020 into the future. So we need not only to think about cleaner energy sources and feedstocks, we also need to think about enhancing resource utilization. So yes, there are things we can do to change this picture. Some will be evolutionary. Most of them will be evolutionary because this is the trend of the industry and society. And some may be more revolutionary if new technologies come into play. But two things that we can immediately do is, and this I'll start from point number 2, is we can improve the efficiency of existing energy technologies. That will already create a much more cleaner and situation as we move forward. The other important factor, of course, is the increasing penetration of cleaner and renewable energy sources. I will put natural gas in this category as well, solar, wind, biomass, geothermal, all of the above. So issues related to CO2 capture and utilization, heat, power, and water integration, we need to think in tandem with food and water, process intensification, which relates to efficiency. All of these are opportunities to understand how we navigate from the primary energy sources to the sinks, in terms of power, chemicals, and so forth. So there are many challenges related to cleaner technologies that I will touch upon, on 2 topics in relation to this. But what are the trends? So 3 trends that we see in the energy revolution, or energy being reshaped, is one is decarbonization, a trend towards decarbonization, a trend towards electrification, and the trend towards digitalization. And these are issues that also, these are aspects that, the trends that also are noted in the headlines. So for instance, even so they might influence investors, they play a role on the share price of companies, and ExxonMobil is an example par excellence of societal impact, along with oil prices decline, of how share prices can go down. But also, all companies, here are 2 examples from Wall Street and Bloomberg Green, that companies like BP and Shell are going towards carbon neutrality. And you see now a lot of circular economy type of aspects in every report of every single company on energy and any other sector. At the same time, digitalization of energy is expected to play, and already is playing a key role. So the ability to harness big data and be able to do a lot of calculations, not only remotely, but in real time on the cloud and so forth, may change the perception of how we can use, let's say, predictive methods and data analytics in order to deliver energy solutions, but also to be able to simulate transition scenarios in the future. So decarbonization is a trend, but it's already taking place. And for instance, in the US, you can see that here is an example of the US power plant emissions, that as a function of time, in terms of various emitters, here you can see that the trend is downwards. This is primarily reflecting the fact that coal power generation is substituted by more modern technologies, mainly natural gas and wind farms. Electric vehicles are also on the rise. The numbers are not very large yet, but clearly we can see a trend towards electrification on the automotive. It remains to be seen, is going to be, if battery-based electrification will be the only solution, or we're going to go towards a scenario, for instance, that Japan is exploring hybrid technologies, where we're going to have hydrogen economy in tandem with some type of batteries. So in understanding, so the key message here is we have all these trends. So obviously there is no magic phone or like a magic button you can press and transform the society from this mega scale energy demand, the mega scale CO2 problems that we have, into a scenario that everything is clean and efficient, right? So my key message of my presentation will be is that as we go through these trends, and regardless how these trends are going to be shaping as a function of time, managing the energy transition holds the key to the success. So the question is, how can we do it in an efficient and in a systematic way? So, and I will be using as an example in my presentation an ongoing collaboration that we have with the Shell as an example where we are navigating scenarios for hydrogen economy, where one of the scenarios can be to produce the so-called dense energy carriers like methanol, ammonia, hydrogen, either in liquid or gaseous form, and then trying to transition from the current scenario, this one on the left-hand side in red, to a scenario which is long-range aim, let's say 2050, 60, 70, and beyond. But obviously, we're not going to be magically transitioning from here to here. We need a hybrid transition period. So it's not only the technologies that we need to assess how they're going to change in terms of scaling up for as the demand is picking up and so forth in terms of maturity, efficiency, and so forth, but also the time scales. You know, can we move? Where are we going to be in 2025, in 2030, 40, and so forth? And you can see here some scenarios. I'll talk about this in a moment. So in taming those, in addressing those challenges in energy, and I'm going to use here just for the purposes, you know, for 2 slides, natural gas utilization. I'm not going to talk about natural gas utilization in this presentation, perhaps in another one, but clearly natural gas is a resource that we cannot really throw out of the window, right? You know, so the US, for instance, has trillions of cubic feet of proven natural gas, you know, and it's picking up. The price is going down, or it remains around 2.7, but the thing is, where and how can we use natural gas, and how we navigate this space of how to utilize natural gas. So, and here is, so if you look at this picture on the left-hand side, obviously natural gas, you can use it for heating, for electricity, but through synthesis gas, it can go to transportation fuels, it can go also to dense energy carriers, aromatics, and the like. So there are many routes that one can explore. So the key challenge is, if one thinks about natural gas utilization, you know, should I go from gas to liquid and so forth, or other kind of pathways? You have many alternatives in terms of technologies, sources, and the right mix. So question is, what is an optimal mix of natural gas conversion technologies? Then another major challenge is, how about developing sustainable energy networks where you explore properly trade-offs between cost, energy, environmental impact, efficiency, and so forth, trying to create win-win scenarios. So an integrated process flow sheet optimization is perhaps a major challenge, along with a proper techno-economic feasibility. And then you have all kinds of value chain and supply chain issues that we need to understand, because it's apparent from this schematic that there is challenges in terms of what is the optimal network of feedstock and product flows, what percentage should go to which destination, which can be dependent on all of these factors here. And the key point I'm trying to make here, in order to be able to address these challenges, we should deploy, if you wish, methods that can reliably show us, you know, provide some quantification of the analysis that we're pursuing. So here, issues related to intensification, process design and control, supply chain, issues related to centralization and uncertainty, supply chain optimization from the field of the process systems engineering can play a role. And that's why I personally push for this holistic approach that is needed to be able to navigate this kind of energy solutions of the system of the future through this multi-scale energy systems engineering. And let me qualify and quantify what I mean. First of all, energy systems engineering sits at the in the middle of modeling all the issues we have from systems engineering tools and methodologies in an attempt to understand and break down the components of the multi-scale challenges, so that we have like at atomistic and molecular modeling, the materials I was talking about, the units, the process design, the value chain. So we need to understand and be able to develop quantitative tools that scale across temporal and spatial scales. And I will use 3 paradigms to demonstrate this, of the validity and need of such an approach towards significantly improving energy efficiency, towards analyzing best options for technology resources mix to meet demands and targets, evolving and receding horizon demands and targets in the future, and towards delivering cost-effective production strategies to meet energy targets. So when we're talking about significantly improving energy efficiency, if you think about a conventional process demonstrated here, and we plot here, just for the sake of argument, this is a metric of annualized cost versus a metric of energy efficiency or environmental impact. If the process is, the structure and the design of the process is fixed, so the only thing we can do is perhaps change so the degrees of freedom we have in the system is about operational degrees of freedom, which then can only explore the trade-offs between improvements of energy and environmental impact, if you wish, but at a price, at a cost. Okay, so this is like a Pareto optimal curve, where every point here is optimal for this fixed structure, but its operation changes, and for that operating point in which you have different emission level and corresponds to different annualized costs. So the challenge is, how can we move this curve to the left, right? Because this is the utopia kind of point. The way to do this is you need to think out of the box and change the design. And that's where process intensification can play a big role. So you move this curve to the left, so that's a win-win now scenario. You reduce simultaneously cost while you improve sustainability, preserve energy resources. That's good. That's exactly the envelope of solutions we would like to do. And we're going to talk about this a little bit further. I'll give you an example for an ongoing, over the last 4 years, ongoing projects we do with the process intensification. The other big challenge, of course, is how you analyze options of the mix I was talking about to meet this moving horizon, this rolling horizon demands and targets. And again, we have a very good basis to begin with. That's where supply chain optimization protocols and methodologies can play a crucial role. And this is something I will talk about later on, but we have done a whole lot of analysis on energy supply chains in terms of gas to liquid processes, hydrogen economy, I will talk about it a little bit more, for generation systems and the like. And the third component of the multi-scale energy systems engineering is the ability not only to analyze supply chains at the macroscopic level, but then to go at the detail level through process design, synthesis, and optimization to be able to come up with verifiable value chains and process designs that can deliver the benefits I was describing. And I will demonstrate this, with studies that we have done on the ammonia methanol co-production, but it will be also becoming apparent from the examples I'm going to use later on. And this is pretty much our vision of the multi-scale energy systems engineering. We do not claim that one technology is going to be the winner, No, we develop the methodological tools and these multi-scale energy systems, engineering framework, protocol, and tools that will allow people to assess and navigate energy solutions of the future and pick the winners of their choice based on the economic, environmental, sustainability criteria of a particular region that we're talking about. There have been a few books. So let me start by giving you two concrete areas really where of the components to show the scope and power of multi-scale energy systems. So I'm going to talk about process intensification a little bit, and then about renewable resource utilization in the context of renewable and hydrogen economy. All right, and the emphasis on process intensification will be mostly on the efficiency side of things. So can we come up with novel design and structures that will allow us to create win-win scenarios? And the emphasis here will be mostly on the value chain and supply chain, so that you will appreciate different scales if you wish. So process intensification obviously has been with us for a while, and already has been applied to a limited extent in an industrial context, like Dow we're collaborating with Dow Chemical, and they have many instances of successful, like divide wall column instances and so forth and so on, simulate moving bench, membrane reactors. So you have all kinds, and there are many patterns as I saw here. So and there is an overview paper that we collated back in 2018 that you can see, that has like over 800 references. So the way one has to think about process intensification is multi-attribute, so you can think about process intensification as means to combine multiple tasks into a single unit. We'll talk about this later. Discovery of novel multifunctional materials that create solutions perhaps from a three-step reaction into one-step reaction if it is a catalyst. Tight material energy integration, that's also an aspect of, because that can increase efficiency. Process equipment miniaturization, so modularity, if you wish, can be, so instead of thinking about scaling up, we can think about numbering up modular units, which we can control efficiency and energy consumption, and then we multiply this. And then how we can think about changing operating modes. For instance, can we, through periodicity or by rotation, increase the efficiency? Examples of this. And enhancement of driving forces, which will be either by materials or like mass heat transfer kind of consideration. So, and you would like to, so these pathways you are doing in order to achieve improve energy efficiency, reduce emissions, so win-win scenarios if you wish, reduce cost, waste, emissions, increase efficiency, productivity, safety, sustainability, and so forth. So there are, but that's a very nice, if you wish, vision, but the reality is there are many gaps. And one of the gaps that the Rapid Institute, Process Intensification Institute, has highlighted is that there are not tools. There are not, okay, we have a very powerful simulation tools at the moment. As you know, some of you know, I have been one of the co-owners of Process Systems Enterprise, the founders of Process Systems Enterprise and the ZPROMS package. But take a package like ZPROMS, Aspen, and so forth, they don't have process intensification synthesis capabilities, right? And we need this in order to be able to discover out-of-the-box solutions. Similar, there is a lack of operability consistently to go from process simulation to doing control, safety analysis, and this type of things in a seamless way. There are no tools that do this automatically yet. And there is a lack of systematic PI design methodologies. So the project that we have put in place and we have been working with colleagues from industry. So we have Dow and Shell. We have Process Systems Enterprise as the software collaborator. And then we have Georgia Tech and University of Auburn. So we're looking into creating three suites that talk to each other, a process synthesis suite for process intensification, that where you can discover a unit without postulating and declaring a unit in advance, an operability analysis suite where as soon as you discover or you declare units here, you can immediately seamlessly go all the way to deliver certificates of operability for the particular structure that you have developed, and then validate it, what we call a model library suite, validated models, both steady state, dynamic, of various, of validated also from reduced order models that people can use so that they can validate the structures they're getting here in order to do properly the analysis at the operability level. So this is, if you wish, the entire program. I'm not going to spend a lot of time. So I talked about the synthesis capabilities, the operability capabilities, and in tandem to this, we're also creating with a lot of supporting material for training and software prototypes. But let me give you some clues of what is behind all this. So the first question we have asked, and it's a challenge at the process synthesis level, is how to systematically derive innovation in intensified design. We're talking about in silico type of thinking, you know, like how you can do prediction in an intelligent way through data analytics techniques, where you declare the unit and the flow sheet from descriptions or at the phenomenal level. So you go from phenomena to tasks and then to equipment. And the key is how you can think about what is the key criterion that drives the system towards intensification, how you define performance limits. And for this, what we have been blowing are some driving force constraints, which have a Gibbs free energy, if you see, so they have the classical terms to exploit the ultimate thermodynamic kinetic space. We don't enforce equilibrium, but we have this to drive the process towards structures, selection of tasks, and for forming equipment by manipulating this, exploring this driving force constraint space. So as an example here, I present, here is the so-called generalized modular representation framework. It's purely phenomena based. So this is the building blocks. So you have a heat transfer block and a mass heat transfer block that then if you put, so this is, think of this like, putting, you put these modules together, and then by putting those modules together and building these driving force constraints, then you start getting things like, without postulating them, you can get a system like a structure like reactive absorption, or a plate like this, like a divided wall, or a reactive separation, and so forth. So just to get a feeling of how this is done, so this is like, and obviously in doing this, you can not only unravel intensified process alternative, but also recover the conventional one. So here is an example, for instance, of an elephant metathesis for butene and hexane production. So you have as raw material pantene, you want to produce butene and hexane at these specifications. So the way we do this, we put these building blocks together, so like Legos, if you wish, and then from a superset of those, like we postulate 8 of those mass heat exchange modules and 16 of these heat modules, and then we put them together. So we allow connectivity amongst this, we create a mathematical model, and then we solve, and then guess what? This is what magically comes out of this by putting everything together. you by picking a subset of those superset of modules, once through this particular realization, that's one solution. This is the conventional process. So it picks one block of a mass heat transfer of liquid-liquid, this is like two separators, and this is one that it picks, like a structure that has both reactive components and non-reactive components. And that's 70% cost reduction compared to this. And then you can go and verify that. So you start from this Lego representation, if you wish, and then you go and you ask, can this be correct? You go then and you validate this, let's say through Aspen, as shown here, or GPROMS, whatever your choice of software packages, and you can see that it validates that this is a much better configuration compared to the sequence then. And then you can go a step further, for instance, and ask the question, how can you explore whether agents can enhance efficiency from a process intensification point of view? Here is an example where we try to identify a suitable solvent for an ethanol water extractive separation within the same representation. So, and we select among two solvents, the ethyl glycol, which is a conventional one, and one based on an ionic liquid shown here, to achieve this type of, if you wish, purity on the ethanol side. And then again, the representation has the ability, again, through these expressions in the Gibbs free energy. So, because there are terms that are functions of the material or the solvent in this particular case. So what comes from this, out from this Lego, this structural representation is one design, which uses the conventional. So here is the conventional solvent, and this is the ionic liquid, which is much better compared to the conventional one. And then again, you can go back and verify. Then you can take now these verifiable designs, and then you ask the question, will they actually work? So can we provide, in addition of steady state consideration, some certificates of guaranteed operation at the dynamic and changing condition? So what we do next is we take those designs or the candidate designs that come out of the synthesis representation, and then we start incorporating flexibility and risk criteria into the same mathematical model. And without going into the details, you can find those in papers. And there is a forthcoming book that we're compiling with Elsevier on the topic. This is the single point optimal design. And then you can see the evolution. This is the reactive separation. You see with five, with two reactive and three non-reactive stages. Here, as you increase the feasible operation and you put stricter criteria in terms of risk, the tendency of the system is to become smaller, and this is what is happening. But then if you keep on increasing the risk criteria and the feasibility range, then the process, the evolution of the structure goes towards having a side unit. And you can verify this. So you go from a 17-tray reactive distillation column to a 15-tray reactive distillation column to 15-tray reactive Patelag type of column to be able to absorb both the risk, the high risk considerations and the feasibility in terms of the operation rate. And then you can take this even further to incorporate directly into the criteria design of model predictive control structures or PI structures using our own parametric optimization and control framework. And just to see here, you can improve. I don't want to go into the mathematics, but here this is the reactive separation system. you introduce disturbances and very high specifications, and then you ask, can you design simultaneously the design and its control structure for this? And indeed, you can see here in the right-hand side an example where the base case has been in a way intensified and explores the interactions of design and control, and the cost in fact goes down. This is counterintuitive, so the integrated design, control, and operable system performs better than the conventional law. And so this is, if you wish, a framework that allows you to do all these kind of steps in a synchronized way. So it's not that you press a button, obviously as you would expect. It's more like a set. It's what I call a prototype at the moment, but it's like a suite of tools that talk to each other and dance together. So here is the process synthesis part. Then it creates designs that they are validated at steady state. It goes to model libraries, so it updates the models because we start from, if you wish, very coarse type of models, then it becomes more like high fidelity type of models, which then it validates through various criteria. So you can, with a different type of criteria in place, so you can do, I saw safety, risk, and economics. You can do life cycle assessment. You can have directly criteria for CO2 emissions and the like. So just an example of a multi-scale energy system engineering approach to process intensification with the key objective to increase energy efficiency and resources utilization. So let me switch gears now and give you another broad example of the power of multi-scale energy systems engineering approach in the context of renewable resource utilization. So when we talk about renewable resources, obviously we need to think very careful where are those resources are. And so for instance, I saw here maps in the US in terms of solar, wind speed, solar intensity, where the crop residues pretty much are distributed in the US, and where the forest residues are in the US. And one thing that one has to keep in mind, and because there are many people who are pushing, let's go for renewables immediately and so forth. So lesson number one is that they are distributed, and unevenly distributed, and they are available in many forms in different parts of the world. So it's a challenge that we need to overcome. How we overcome the uneven distribution, so you don't have it exactly where you want. The other important and clear, not only that you don't have it where you want it, perhaps the destination of the use is also might be geographically on the opposite side of where the solar density, for instance, intensity occurs, right? And I will show you examples of this later on. So that's challenge number one. Challenge number two is so it's not only the supply-demand mismatch, it's also the variability in terms of intermittency, right? So here I show in the left side of the slide, the wind speed variability and the solar intensity variability in the area that where Texas A&M is and Brazos Valley, Texas. So here is like just daily variations of the wind, and you can see during 5 successive days in July, so huge variability. And then solar variability over seasons, and Texas, like Saudi Arabia, is a place blessed with the sun, right? And still there is seasonal variability. And that creates, that's problematic. This mismatch is problematic because it can create, at least in terms of the energy, like in electricity provision, the so-called ducker, right? So if you think about having power generators that are only rely on renewable, you have to acknowledge that this intermittency, so you need something like, you need to prevent this, you need what? You need storage, right? So storage then becomes important. And then there is a question, is this an adventure in storage? And how you mitigate this resource variability in an effective way, right? When we talk about energy storage, it's also important to think a little bit more in depth, right? You know, so here just an analysis, not an exclusive analysis of various energy storage technologies, if you wish, and the scale, maximum storage duration, and some of their properties, right? And what I would like to draw your attention, especially if you focus on this part of this table, is, and obviously these features here, you know, these parameters and properties improve as a function of time and as the technologies improve. But pretty much, you know, from a both volumetric and gravimetric energy density point of view, current battery technology is not the most efficient, right? The other is that, and in terms of maximum storage duration, we're talking hours. So maybe rethinking hydrogen and dense energy carriers like ammonia or methanol, which have much better properties in terms of maximum storage duration, look at the density, both volumetric and so forth. And, you know, like thinking something like ammonia, in fact, and methanol is better compared to, you know, like even to liquid hydrogen, right? So, you know, these are, so there is a question, will dense energy carriers can they offer cheaper storage and mobility over batteries? And how can we explore this in a hydrogen economy landscape? So I'm going to revisit the problem that I said earlier as part of our studies. It's an example to demonstrate how you analyze this. So the emphasis is not on the net result, because that will depend on cost criteria, on maturity of technologies, evolution of risk, and so forth, the risk. But I want to use this as an example of how multi-scale energy systems engineering, the methodologies and the tools can help us navigate those challenges and look at those transitions in a systematic way. So first of all, you know, from a modeling representation point of view, we can use supply chain optimization concepts to look at where various candidate facility locations exist, solar availabilities, wind availabilities, even water, CO2 point resources, the transportation issues, the demand, and we can then build on those supply chain models, detail, you know, parameters that will come from the design, detailed design analysis for hydrogen production, ammonia production, methanol production, and so forth. And to demonstrate how this is an exam, a comprehensive exam, which we are allowed to publish. So this has been published and you can look at the details, where it looks at this is joint, again, work with cell. So where we look at the following scenario, right? So what if we look at trying to substitute 10% of the year or on the annual New York City power demand using renewable energy, both base case and we'll see also the load following, by looking at three scenarios. One, that we produce and ship dense energy carriers in Amarillo. I will show you why Amarillo is in the northwest side of Texas, where the wind is always blowing and the sun is always shining, and then ship it out to New York City and then transform it into electricity through converting the dense energy carriers, versus a scenario where everything is produced in New York City. Obviously, this will only be solar and energy and solar and wind and batteries. And you need to find, obviously it's not going to be in Manhattan, so you need to find the location of where you're going to put all this. and then a hybrid scenario where you monetize the local production through dense energy carriers, right? And you do this to meet the electricity demand on levelized cost of energy. So we look at various options, and you can, I mean, now we have tools to do to look at more. So so we look both at the base case, so an average scenario, as well as following the curve type of scenario. So the questions we want to answer is, can we use the high renewable potential in Texas to partially power a city in the Northeast? Can we use energy carriers to transport renewable energy from Texas to Northeast? How will this compare against using local renewable potential and battery storage in the Northeast? And what should be the targeted energy demand? What is the optimal mix in a hybrid scenario? And this problem can be generalized, obviously. And so from a multi-scale energy systems engineering point of view, so you can think about having a location A or a number of locations which are high in renewable potential, and you have location B, which might have low renewable potential in terms of, you can see here, and then you produce locally, but there might not be a lot of population here. So you produce what you locally need, and then you ship the rest into the other areas which are not equally blessed, right? So this is the scenario we built. So we look at the inputs. Process network can have local battery storage or battery storage in any other location. Dense energy carrier productions, obviously, you have solar and wind farms. Then you can produce dense energy carriers to power for local, or you transport the dense energy carriers, and you do this in hybrid mode, either fully or in conjunction with local solar and wind kind of scenarios. Right. All right. So, and the tools we employ in order to be able to address such a multi-scale problem is supply chain concepts together with detailed process synthesis and design optimization in tandem with scheduling. And why scheduling? Because, as I said earlier, wind, and I'll come back to this, wind and solar, there is this intermittency kind. So you need to make sure that the system works at the hourly or minute level, right? And we develop a mega model which has the form of, which preserves linearity. So we develop reduced models which are linear, and we have zero variables to navigate the various options. We call this problem mixed integer linear programming problem. So how we develop, just to give you some flavor of how this is done. So this is the level of detail. We look at the process network level. You can see the, the materials flow. You can see the energy flows in red, where we have storable energy resources in, here, storable material resources. We have the detail, I have boxes, air separation, electrolytes, and methanol synthesis. Behind this is the detailed simulation, the nitty-gritty details. So we have the fuels production, and you can generalize also to simultaneous power and fuels and chemicals. So you have the hydrogen generation, you have the power generation, the methane conversion technologies, the fuel production, and so forth. So we are building models at a very high fidelity level, from which then we reduce the complexity through data analytics techniques to derive linear models within certain bounds, which then we embed into the overall optimization model. So obviously, we create large-scale optimization problems. You can see here, if you preserve nonlinearities, this is a very large-scale type of problem, and you can find some details in our publication. But then to be able to incorporate in this mathematical modeling paradigm also the intermittency component, so that you need to look at the time domain as well, you need to create linear models. So which we do, as I said, by taking this input out, by looking at this type of models, which are, this is the simulate models, high fidelity models, looking input output, and we develop linear input out relations of the various parameters of interest. And just, so this is from, for those of you who do research, let's say in the scheduling or process systems engineering area, this, so we utilize, so this is like a discrete time resource task network representation, right? Which is very powerful. This RTN representation is very powerful, and where you can use, you have network synthesis components, the operating mode selections, inventory balances, and you navigate this through the judicious choice of the 0-1 variable. So that's on the modeling side. So how about the scheduling side? Remember that, you know, there is intermittency, so there is a variability over hour or even minutes sometimes, right? So how you tame this? So how you are able to solve simultaneously this supply chain problem, the design problem, the operational problem for 36.5 days? It's almost impossible to do it even for the linear modeling side, despite the advances in computing. So you need somehow to aggregate now the time representation. And for this, what we do is we employ machine learning type of techniques. So here is an example where we use agglomerative hierarchical clustering type of techniques, which preserve the time chronology and which allow us to reduce from the time representation from 365 days to a minimum number of representative days. For instance, you can see here that within 10, 15 clusters, instead of 365, the accuracy is close enough. So we use, let's say, 15 representative days, time spots, if you wish, which allow us to be able to solve this type of problem. And here are some indicative outcomes of such a multi-scale energy systems engineering. We have done, we can solve hundreds of scenarios, but here is one just to get a flavor of what you get. And this, so I was talking about two scenarios, the base case as well as following the curve, right? So does the technology change? What is, how can we, obviously from a modeling point of view, this is a much more demanding, and that's why I'm showing it. Okay, the three scenarios that that I was talking about earlier. So here is I'll just glance through this just to get a feeling. So, and the comparison basis, we have done also CO2, you can extrapolate, you can do many things, but what I'm showing here is levelized cost of energy. Let's say the cost of electricity per kilowatt hours, right? So that's a good comparison basis. So here is local PV versus dense energy carriers for the base load. If you produce everything in New York State, 0.284. If you transport everything from Texas, 0.289. Clearly, both, just to give you, so the levelized cost of electricity, right now, you need to break this close to 0.1 to 0.12 to be for a consumer to be happy paying, right? Because you don't want to triple your electricity bill. But look at that, the hybrid model, where you find the optimal amount that you ship from Texas and ship it and bring it to the local market in conjunction with solar production in locally can bring the cost down to 0.153. Okay, obviously the costs are indicative here because they depend on a lot of assumptions and so forth, but when you are at 0.15 region, now this becomes attractive. So something that perhaps with as technologies become better, efficiency becomes better, better use of materials and so forth, it's expected this will go down even further. And if you do the analysis for peak saving, which is much more demanding, again, the local scenario and the transporting from Texas are not very appealing. However, look at this. Again, another hybrid scenario now, where you produce from wind. Texas, we are leaders in wind farms, and all our analysis shows that in Texas, the best renewable technology for the current technology and prices is wind. And that's why 18% of the electricity from Texas comes from the wind farms. So it picks wind, all of those are renewable technologies. It ships this amount of hydrogen through a dense energy carrier, and local production here, the price goes down to 0.13. Now you're talking, now this is the close to something that, for instance, this is not very far for what the electricity price of, for instance, in California is. So therefore, this is something that society can accept as a function of time. And this is a tremendously, renewable technology. And here is a summary, don't take the numbers as this is the panacea to happiness, are indicative, and we're interested more on the relative kind of, so here are scenarios which look attractive for the base case, and this for the peak saving. And behind this, we have complete validated designs, pathways, and so forth, and simulation results to back off from a risk analysis to this type of quantification. So let me summarize this part, and also through this analysis, you understand where are the, where are your largest contributors of the cost are, is that the production of the wind and solar power production, these are very costly. And in all our analysis, and this is not counterintuitive, this is what I was expecting, controlling the mix of both the sources and the sinks is important, so, and this is what this type of multi-scale energy systems approach can be very helpful to. So just to revamp of what I talked about, I gave you a flavor of, at a glance, what the Texas A&M Energy Institute you were talking about, a little bit about my own research activities, and then I focused on what, like this area of what we call broadly multi-scale energy systems engineering. I gave you key challenges, the methodological framework, and then I demonstrated this through two areas, if you wish, on process intensification and optimal energy transition strategies. Thank you very much. This ends my presentation. Thank you for staying so late. I'm grateful. I hope I have not, it was worth it staying so late. And I'm very grateful for the invitation again, and I'm happy to take any questions and address them if there are any. Thank you.
Thank you, Professor. That was a very nice and very interesting and impressive, actually, presentation. So thank you so much for this. Okay, so let's start with questions. Gentlemen, please raise your hand and we're going to call your name.
Yes, and as I said, I can send also the slides, a PDF form, so that we can distribute to people who are interested. We would like to, as part of our ongoing collaboration, and as a first step, it would be great. I'm happy to send my slides.
Perfect. Thank you so much. We actually appreciate this a lot. It would be helpful to have the slides and refer to some of the references that you showed.
And if there are questions in terms of references and so forth, you can go also into my website and you can see some of those. In the modern era, nothing is hidden, right?
Yes. Okay, so gentlemen, any questions?
And I will encourage students to give, to ask questions.
Yeah, actually, we have one of our students in renewable energy who would like to ask a question.
And it's and I hope they appreciate it. Obviously, we all know the complexity of the problem, and we also know that there are different schools of thought. There are people who are pushing for a particular technology, and that's exactly my point. We need quantitative tools that will allow us not to put all our money on, when even from an investment point of view, you don't want to invest in the wrong technology, right?
Yeah, you don't want to put all eggs in one basket.
Exactly.
Okay, so Hussein, go ahead, sir.
Yes, thank you very much, Dr. Stratus, for a very interesting presentation. My question is, here in Saudi Arabia, we have a great potential for investing in the solar energy, but at the same time, regarding the PV technology, the photovoltaic technology, we are facing a problem with the heat due to the fact that its efficiency drops dramatically during the day because of the heat. It can reach like 80 or Celsius or maybe more. So what do you think the possible solutions to solve this and get a good efficiency?
I'm not a materials expert, but the new materials, I saw some reports that the new materials now that they are the petrovites and support, some of those are have the property that their efficiency doesn't drop during the night. So one way is, I'm sure this, first of all, I completely agree with you that Saudi Arabia is blessed with sun, first of all, and I've seen already investment like Aramco on ammonia and shipping to Japan and so forth, and so that's tremendous direction. Now, obviously, solar still, we need to understand a little bit more in depth the reliability of the materials, right? So it's a materials issue, but I'm optimistic looking at the properties. They are efficient as efficiency increases. Like now, the maximum efficiency of solar is, it's around 22-24%. If it reaches 40-45 with the new materials, and I mean, obviously, we'll take that perhaps, and if they withstand a little bit more the temperature increase, but their efficiency doesn't drop when, like if there is so much, so, like that might be one way to, and then obviously, and again, I wouldn't put, for instance, why Texas is not investing heavily on solar as much, because whereas California, for instance, invests heavily on solars, right? Two things. The answer, this depends on two key factors, at least locally in the US. I mean, different states have different characteristics, right? So in Texas, first of all, the electricity price is very low, right? Which makes the solar alternative more expensive. So, whereas the wind is much more efficient, and, we at the moment, as I said, 18% of the electricity comes from wind, right? Now in California, the electricity price is almost twice as expensive. So our folks, our colleagues in California pay a huge premium. I mean, it's not exactly twice, but it's like 60% more expensive, right? Compared to Texas, right? So at that cost, solar is very, can be, it's a suitable technology. I think also for for a country like Saudi Arabia, hydrogen will be key, in my opinion, because you are blessed with the, again, because of solar, from solar you go to hydrogen and so forth. Some of the examples I saw could be, and ammonia, I have done, I don't want to again single out a single technology, but ammonia, all our studies show that liquid hydrogen and ammonia deserve further technique. We need to look a little bit more in depth. I know I have not answered your question directly, but I gave the answer. I cannot hear.
What you are doing right now is actually exactly what NEOM is trying to do, which is to produce green ammonia from solar energy. And can you hear me, Professor?
Yes.
Yeah. I was saying that what you're doing is exactly what NEOM is trying to do as part of Vision 2030, which is to produce green ammonia from renewable energy, solar and wind, and basically use this ammonia as a long distance hydrogen carrier, and so on. And as you said,
and we're involved. Yes, and we're involved in studies. I didn't have time to go because obviously production of hydrogen should be green product, so it has to be green as well. So, but we look at, so how we can, and in Texas, we're producing a lot of hydrogen, but mostly from fossil fuels, right? So, and we're looking of ways to transform this, so go into a mix of green production of hydrogen and ship hydrogen directly to California, for instance. We're looking in this type of studies as well.
Okay, by the way, okay, right now we can see you. Okay, so we have a question from actually an Aggie. He's a Texas A&M graduate.
All right.
So Dr. Eid, please go ahead.
And you can see my Aggie tie at my, you cannot see my Aggie, pins.
Yeah.
Howdy, Professor Stokovic.
Howdy.
Yeah, how this is Leader Muteri, Associate Professor with the department, and an Aggie as well. I have, thank you for this presentation. It's very interesting, especially for people who are process systems and interested in energy. I just wonder about the problems you have shown regarding different solutions or different optimization solutions that you proposed. What are the how are the sophisticated problems they are when it comes to solution? Are they, you showed MINLP, some other also problems with high non-linearity problems, but about the complexity and how you were able to solve all of these problems. If you could elaborate on the solution method.
Let me highlight a few points here. Many thanks for the question and support. So first of all, I would like to emphasize that such a multi-scale energy systems engineering, obviously has a lot of process systems engineering components, but it's meant to be supporting also colleagues who are working on the entire spectrum of energy research, because very often you see people working on monolithically in one technology, or they're pushing one technology, and as industry considers transitions in new modes of operation, it's important that we provide to them quantitative tools that they can analyze those options on an apple-to-apple basis and not on an apple-to-orange basis. Hence, the need for such a holistic approach that I highlight. So that's point number one. Number two, now obviously the devil, very correctly you pointed out, depends on the detail. So, and that's why I put a lot of emphasis in my presentation on how you construct this framework that I highlighted. So So these are not macroeconomic type of models, because macroeconomic type of models, garbage in, garbage out. They're not going to capture technical feasibility. So we start with models at the level of, like building blocks of what you would do in a typical simulation and try to validate, like when you talk about electrolyzer, this, all the production facilities, and then we extract simpler models from this, which then you can go back and cross-validate, because the cross-validation is it. And then, obviously, unavoidably, we create very large-scale optimization models, which, even with our sophisticated tools, they are not solvable yet, right? So that's why, especially when you have the time representation, when you try to navigate the entire time space. So, and then we use some solution methods which allow us to solve this type of problems. I'm happy to report, despite all this, I'm happy to report that we can solve now quite realistic problems, and we are testing this with our cell colleagues. We're testing some scenarios that are, I could report, they are testing, I suppose we are testing, so they are quite large scale, and with the tools that we're building, we're using, for solving this large scale MILP problems, we're using Gurobi and some greedy, some heuristics to be able to solve. Yes, we're using sophisticated tools, but these tools will become available, and hopefully industry and colleagues around the globe will be able to use them.
Any other questions before I end the seminar with 2 questions from my side? If there are no more questions. Okay, so let me ask 2 questions. And myself, I'm an owl. I'm a Rice graduate, so I'm still from Texas, but arrival.
We take a pan-Texan approach to things.
Yeah. So basically, my first question is that, for example, in your ethanol water ionic liquid example, this is a tough system to model from a thermodynamic phase equilibrium point of view. So, I mean, how accurate are the optimization models, or not how accurate, how sensitive are the optimization models to the uncertainty and the thermodynamic models that were used to model the phase equilibrium and the transport properties also?
Very good, very excellent point. Excellent question. Let me see, where was this? There, yes, okay. I want to emphasize what is the objective of the process synthesis representation, right? So we are using these blocks essentially. So here the objective is not to create fully validated systems. It's try to explore you ask the question, are there other possibilities? For instance, is there exist another solver that might be better than the conventional one? All right, and what will be the derived structure of this? And then you go and you validate with, this is simulation now. So so the objective here is just to get unexpected solutions that you might have never postulated in advance. Okay, here there are only 2 options, but I was giving an example. You might have a set of solvents to play with, right? So and then so this is more like a coarse type of representation. So we're only using this type of expressions, this expression. So this expression, we don't make any assumption. Obviously, what type of thermophysical properties we're going to use, from which libraries goes there. But I mean, this is the exact equation, right? So the point is that we are using quite a detailed model for the thermodynamic kinetic. Obviously, we don't do analysis, we don't do CFD analysis or kind of things like this, but we need to understand what we're trying to do here is not to do a detailed design of equipment, is trying to ask the question, is reactive distillation better? Could it be better than sequence of reactors and separators, and under which conditions? This is what the type of analysis we're trying to do. And then the analysis after this allows you to dig in, as is highlighted here, to the level of beating it to death with very detailed dynamic model. So you go stepwise, in other words.
Okay, so
can you speak up a little bit? Yeah.
So I guess this is still related to the first question. So how detailed did you model your reactors? Was it like two-dimensional 1D, 2D?
Yeah, or yeah, very good point. Yes. For instance, now we are we can go all the way to. Usually we do simplified 1D models, right, for reactor model. But for instance, now we're working on a project with trying to expand this to microreactors. So we're working together with Dion Vlachos from University of Delaware and their teams there. And they are using very sophisticated models, to the level, as you may know, right? And so at the level of the synthesis, you don't need. So from their detailed models, we approximate through aggregate models, which we incorporate the synthesis model. We check the trends of the system at the outcome of the synthesis, and then we validate at the simulation level, which can go all the way to very detailed 2D model simulation.
Okay, my last question is, did you consider the dense energy carrier storage in your simulation? Like,
sorry?
Did you consider the storage of hydrogen or ammonia in your optimization problems and their effect on the cost?
Very good point. Yeah, in these models, we take into consideration also the transportation. Yes, there's a transportation cost, which I didn't talk about. So so here if you see, so there is so you have the production here, as you see.
Yeah. And
then you put it in a train or something, and that's essentially this transportation cost is included in the model. And our analysis shows that at least for this type of system, strictly because the cost of production is very high, relatively speaking, the cost of transportation is not that high. So in other words, the transportation is the storage device as well. That's all I'm saying. So we're looking at so if you do liquid hydrogen, for instance, and you transport, that's your storage and transportation together.
Perfect, Professor. This was a really very nice presentation and really a very nice discussion. So again, we appreciate that you accepted our invitation so much, and that you give us some of your time to share the work that your group has been doing. And we hope to stay in touch in the future and maybe invite you soon after the pandemic ends, hopefully, to visit us in Saudi Arabia and hopefully start a very fruitful collaboration with you and with Texas
and vice versa. And vice versa, I would like to extend, it would be great to welcome a delegation here and explore ways for us to build further relations with students, joint students, projects, and so forth. So I will welcome this opportunity I would like to thank you for hosting me. I would like to thank the 42 participants that stayed awake until this time. That's impressive. We started from approximately 80 people, so that's good, you know. So thank you very much, and we'll stay in touch. Thank you.
Okay, have a good day, everyone. Thank you.
Bye-bye.
Good night.
Bye.
Bye.